everyone, I'm Chen from Tianjin University. It's a pleasure to share our research on marine code naturalness with you today. Human beings use natural language to communicate. One of the key characteristics of natural language is its naturalness, which refers to its repetitive and predictable pattern. People tend to reuse familiar expressions rather than invent new ones. And this predictability allows us to anticipate what comes next based on the given language prefix. This feature has been widely exploited in various NLP tasks. Hello everyone, I'm Chen from Tianjin University. It's a pleasure to share our research on marine code naturalness with you today. Human beings use natural language to communicate. One of the key characteristics of natural language is its naturalness, which refers to its repetitive and predictable pattern. People tend to reuse familiar expressions rather than invent new ones. And this predictability allows us to anticipate what comes next based on the given language prefix. This feature has been widely exploited in various NLP tasks, such as text classification and text generation. Inspired by the naturalness of human language, researchers have found that programming languages also exhibit similar repetitive and predictable patterns. This concept, known as code naturalness, has been widely employed in a range of tasks in software engineering, such as code generation and code completion. It also forms the basis for the rapid development of statistical language models for source code. Given the significance of code naturalness, accurately measuring it has become an important research problem. Ray et al. Proposed using a cached n-gram model to calculate the entropy score of code and normalize the score based on different statement types. The normalized entropy score then serves as a measure of naturalness. To address the limitations of n-gram models, such as being trained on smaller datasets and struggling with cross-project scenarios, Canford al. introduced CodeBird NT, which leverages the pre-trained CodeBird to predict mask tokens within each code line and leverages the prediction confidence as a measured naturalness. Although code naturalness can be measured more precisely with these methods, both of them measure the naturalness of each line of code in isolation. The problem is the code is rarely understood line by line in isolation. They often depend on other code lines, and humans rely on the relationships between code lines to understand the code. Ignoring these dependencies can negatively impact the measurement of code naturalness. And incorporating code dependencies may provide a more accurate measure of naturalness. Inspired by this, we developed DAN, which integrates code dependencies to offer a more precise measurement of code naturalness. DAN first constructs a program dependency graph using data flow and control flow analysis. It then collects all the passes in the graph. Then, to reduce noise in the extracted passes, then further extract n-node subsequences. Finally, then measures the naturalness of each subsequence and averages them to determine the naturalness of the entire code snippet. Next, let me walk you through the technical details. To extract dependency information from a given code snippet, then transforms the code into a PDG representing the control and data flow dependencies among program elements. Then constructs the PDG as a granularity of program statements. For example, given this code snippet, then generates the corresponding PDG like this. To incorporate dependency information into measuring code naturalness, then extracts passes from the PDG using a depth-first search strategy. Starting from a designated node, DFS explores each path in the graph systematically. However, complete passes tend to be long and complex. They often have many overlapping nodes. This could introduce much noise and increase the computational overhead. Dan addresses this by extracting n-node subpasses from each complete path. For instance, when n equals to 3, 4 distinct subpasses can be extracted from the 3 complete passes in this graph. Then leverages statistical models to measure the naturalness for each subsequence and average the naturalness measured for each subsequence as a naturalness of the whole code snippet. We conducted an empirical study to investigate whether incorporating code dependencies can improve the measurement of code naturalness. We evaluated DAN in 3 key scenarios, including its core task of distinguishing natural and unnatural code, and 2 applications of code naturalness: identifying buggy code lines and cleansing data for training code generation models. For comparison, we chose the ngram NT and CodeBird NT methods, which I introduced earlier. Additionally, we included an approach named CSN. CSN considers all code lines together in a sequential manner, which can include all dependencies information in the code snippet. But CSN can incur much noise in code dependencies. Hence, we improve CSN by splitting the complete sequence into a set of n-line subsequences, then measuring the naturalness of each n-line subsequence. We call it CSN sub. We instantiated DAN CSN and CSN sub using both ngram and CodeBird models, respectively. To address RQ1, we need a dataset of both natural and unnatural code. We treated the Human Evil X dataset as a natural code. Human Evil X consists of 164 handwritten programming problems and the corresponding answers. which has been widely used as a reference to evaluate code quality. We transformed each natural code into unnatural code using 3 transformation rules: dead code insertion, confusing code insertion, and variable renaming. For example, dead code insertion randomly inserts blocks of code that will never be executed. Confusing code insertion inserts code that, while executable, does not alter the original functionality. Lastly, variable renaming replaces meaningful variable names with meaningless ones. For each piece of natural code, we applied a transformation rule to create 4 distinct versions, each exhibiting different degrees of denaturalization. To evaluate how well Dan distinguishes between natural and unnatural code, we measured the naturalness of each piece of code and its transformed counterpart. We then calculated the normalized difference in naturalness between each pair. Our results show that Dan n-gram outperforms n-gram NT and Dan CodeBird outperforms CodeBird NT across different levels of unnatural code produced by the transformation rules. Specifically, Dan n-gram improves upon n-gram NT by an average of 41%, while Dan CodeBird shows a 13-fold improvement over CodeBird NT, based on average normalized differences values across the 12 sets of unnatural code. Notably, CodeBird NT even incorrectly identified some unnatural code as more natural. Moreover, Dan n-gram outperforms CSN sub n-gram and Dan CodeBird surpasses CSN sub CodeBird in most cases. On average, Dan n-gram shows a 58% improvement over CSN sub n-gram, while Dan CodeBird exhibits a 136% improvement over CSN sub CodeBird. Furthermore, Dan consistently outperforms CSN, highlighting that incorporating broad dependency information significantly enhances code naturalness measurements compared to merely using the local context. In summary, incorporating code dependency leads to a more effective distinction between natural and unnatural code. This confirms the overall effectiveness of incorporating dependencies for accurate code naturalness measurements. To answer RQ2, we prioritized the lines in buggy files based on their naturalness scores, with higher prioritized lines more likely to be buggy. We used 2 widely adopted metrics, namely RAUC-N and MRR, following the existing studies on prioritization tasks. RAUC-N calculates the radius of the area under the curve for the ideal curve, and MRR is the reciprocal of the rank of the first correctly identified buggy line for each file. We evaluated Dan on 3 datasets commonly used for buggy line prioritization, including Defects4j, Growing Bugs, and Smart Shark. Our results show that Dan n-gram outperforms n-gram NT and Dan CodeBird outperforms CodeBird NT on all datasets across all metrics. For example, Dan n-gram and Dan CodeBird achieved 14 to 28 and 14 to 40 improvements over n-gram NT and CodeBird NT, respectively, in terms of RAUC 20%. And 2% to 6% and 40% to 22% improvements in MRR. Additionally, Dan outperforms CSN sub in all cases. In summary, incorporating code dependencies into the measurement of code naturalness is more effective at identifying buggy lines. To answer RQ3, We selected the top 50% most natural training data to create a cleansed dataset for fine-tuning code generation models. We evaluated the fine-tuned models using two metrics. The first one is code blue, which measures the textual similarity between the generated code and the ground truth code, and it can reflect the readability of the generated code to some degree. And the second one is average pass ratio, which calculates the ratio of passing test cases for each piece of generated code. We leveraged two widely used datasets, namely human evil X and X, to fine-tune two widely used models, including Chen and GPT-2. The table shows the code blue score of each fine-tuned model based on different sets of training data. The raw R presents the result of each fine-tuned model based on all training data in each dataset. And the last 5 rows present the results of each fine-tuned model based on the cleansed training data in each dataset by 5 different methods, respectively. From the table, the fine-tuned model with the aid of Dan can generate code with higher readability than those based on all training data, demonstrating the importance of cleansing training data for model building. Furthermore, both Dan Ngram and Dan Colbert do not make their fine-tuned models sacrifice the overall code generation performance. In terms of the average pass ratio, their fine-tuned models even slightly improve the code generation performance. Our results indicate that incorporating code dependencies with Dan produces cleaner training data, leading to better model performance compared to using all or randomly sampled data. Furthermore, we confirmed that the subpath extraction in Dan indeed reduces the noise present in the complete sequences, which would negatively impact the code naturalness measure. We also demonstrated that Dan can generalize to larger statistical models like CodeLlama. In conclusion, our study demonstrates that incorporating code dependencies significantly enhances the accuracy of measuring code naturalness and boosts its performance on various downstream tasks, including identifying the buggy lines and cleansing training data for building better code generation models. By leveraging program dependency graph and extracting the subpaths, Dan incorporates the code dependencies and the broader contextual information while avoiding the negative impact of the noise for more accurate naturalness measurement. That's all. Thank you for your attention, and I look forward to any questions you may have. Hello.
Testing.
Can you hear me?
Can you hear us?
Yes, I can hear you.
Okay, thank you. We have time for maybe one very quick question. Okay, I'll just ask briefly. So first, thank you for the talk. I'm curious about this notion of code naturalness. I mean, to me as an HCI person, I don't know how you would evaluate naturalness in a sort of well-founded way without actually doing a user study, right? So I guess I'm wondering if you can sort of justify your metric of naturalness in terms of your corpus. Like, why is that a better way of evaluating naturalness than actually asking people to do a study?
You're asking why incorporating codependencies can be a better measurement for co-naturalness, right?
No. I'm asking why the metric of naturalness, why your evaluation method is better than doing a user study, where you actually have people evaluate properties of code. Because to me, naturalness should be about people, right? Natural sounds like it's going to be about people's perceptions.
Okay. As co-naturalness has been applied in some, as I introduced in my presentation, co-naturalness, on one hand, it is about the human perspective. That it means that how humans feel like about a code, whether it is easy to read and easy to understand. This is from the human perspective. But co-naturalness has also been deployed in various downstream tasks, such as identifying code buggy lines. And cleansing the training data for code models. There has been studies which demonstrates that the code with smaller naturalness is tend to be buggy, and there has also been some studies proves that training statistical models with high quality data can improve their performance. And I think co-naturalness can serve as such a quality measure to help us to identify whether the data is high quality or low quality. So I propose to measure co-naturalness accurately to boost these downstream tasks.
Okay, we're out of time. Thank you for your presentation. Thank you for your comments.